Hey, welcome back. This is the review for test 2, basically chapter 8. Uh, so the question pool is listed there, 8.1, 8.2, so you might want to pause the video and copy those down. Those are the WebAssign questions, by the way. So any of those are fair game. Please note we're not doing 8.6. That was the numerical integration section. Hopefully the homework will be enough. Okay, so let's dive in here. I'm going to just hit a couple problems from each section. Usually I'll put similar problems on the test, and then I'll pick a couple from the question pool as well, just to keep you honest, okay? Okay, so let's go to 8.1 first. 8.1 was all about integration. Any of those questions are fair game. So these are U-sub problems. You have to know your basic integral, like the power rule. You have to know all the trig integrals, the inverse trig integrals, so the arctan and the arcsine integral. Problem 3, we see some long division. Basically, when the degree of the numerator is greater than the degree of the denominator, so in this case, the degree stands for the highest exponent you see in the polynomial. So in the numerator, the highest exponent is 2, and the denominator, the highest exponent is 1. So here, the numerator's degree exceeds the denominator's degree, so you do long division. Okay, so we say to ourselves, what times x is x squared? Well, that's just x. Distribute that through the x minus 10. Subtract. So we'll have 10x, and then you say what times x is 10x? So that would be plus 10. So I have 10x minus 100, and then we'll subtract those. So you'll get 10x minus 10x, 0, and then carry that negative in, it's positive 100. And then we use that to rewrite our integrand. Okay, so it'll be x plus 10 plus 100 all over x minus 10. So the integrand turns into x plus 10 plus 100 all over x minus 10. Okay, the first two parts are simple. Those are just, well, the first one's a power rule. And then the second one, the integral of a constant, you just kind of slap an x on there. The third one, you may want to do a u sub. Okay, you can if you want. You'll just do a u sub for x minus 10. du is dx. So I factored out, I factor out 100. And I have then 1 over u times dx, which is now du. So you have x squared over 2 plus 10x plus 100 ln absolute value of u plus c. Then you have x squared over 2 plus 10x plus 100 ln absolute value of x minus 10 plus c. Okay, so fairly simple. Let's look at number 5. So I expect you to have basically all the formulas for integrals, well known. In particular, you should know the arcsine and the arctangent forms. So this one is an arcsine. So you have the integral of 34 all over the square root of 10x minus x squared dx. Okay. So in the denominator, I'm going to have to complete the square. So I have 34 all over, and in order to complete the square here, I need to factor out a negative, right? So I got negative x squared, and then minus 10x, and then I'm going to plus b all over 2 squared. So b is negative 10. Negative 10 over 2 is negative 5. Negative 5 squared is 25. Okay. So technically I've added in negative 25 because there's that negative out there. So to keep it in balance, you have to add 25, and that should be under the square root there. Okay, so at this point then I can go ahead and rewrite. I'll have 34 all over the square root of, and I'm going to do the commutative law to rewrite the 25 first, and then minus x minus 5 squared, and then a big dx over here. Okay, so this form is now our arc sine form, and in particular the u is x minus 5, and then the du is just dx. I don't have to do anything extra there. And then the a value will be 5, right? So I can integrate here. You can factor out the 34 if you want, and then if you want to do your subs, you can. So I have 25 minus u squared, and then dx is just du. So this will be 34 times arc sine of u all over a. So a in this case is 5, and then plus c. And so I get 34 arc sine of u, which is x minus 5 all over 5, and then plus your integration constant. Okay. Okay. We didn't really see too much that was all that new in this section. I mean, I'm pretty sure there was one like number 3 on the test, on the first test. I think the first problem was kind of like that. You had to do long division. Number 5's an arc sine. I expect you to know that on the first test as well. You have to do the arc sines and arc tan formulas. This next one you may not have seen before, this number 10, and that was using a Pythagorean conjugate to kind of turn the denominator from 2 terms into 1 term. Okay, so how did that work? It was a bit like rationalizing the denominator by multiplying by a conjugate, and that's kind of why they call it the Pythagorean conjugate. Okay, so instead of cosine theta minus 1, you're just going to go cosine theta plus 1, cosine theta plus 1 d theta. Okay, and the numerator will have 5 cosine theta plus 5, and the denominator, if you FOIL it out, you'll get cosine squared theta minus cosine plus cosine, so those will cancel, and then minus 1. Okay, then you could use Pythagorean identity to rewrite the denominator, so you would end up with 5 cosine theta plus 5. Cosine squared minus 1 is you have to be a little bit careful, so let's think about this a little bit. So we know sine squared plus cosine squared is equal to 1. So sine squared is equal to 1 minus cosine squared, but that's not what we want, right? We want cosine squared minus 1. So if you just kind of multiply both sides by negatives, you see, oh, that's the cosine squared minus 1 equals negative sine squared. So in the denominator here, you'll have a negative sine squared theta d theta. I'm going to move the negative to the numerator and distribute it. So I get negative 5 cosine theta minus 5 all over sine squared theta d theta. And then I can go ahead and butterfly. Okay, so kind of do this idea, and I'll end up with the integral. Let's factor out the negative 5 of that thing. Cosine theta all over sine squared theta d theta, and then the other guy, negative 5 integral of 1 over sine squared theta d theta. Okay, I need to then turn these guys into something I can work with, something I can integrate. Okay, so if you rewrite cosine over sine squared as cosine over sine times 1 over sine, that's going to do it for you, because that'll give you a cotan times cosecant, and we know that's the derivative of negative cosecant. Okay, the other one, minus 5, 1 over sine squared is the same as cosecant squared. Okay, and then of course the derivative of cotan is, you know, cosecant squared, so the antiderivative. Did I say the? Okay, let's clean them up. Let's clean that first one up and see what it is, and then hopefully we'll know. So I believe I said this was cotan theta times cosecant theta, and then that thing right there is the derivative of negative cosecant. So to get the antiderivative, you just you know, that is negative cosecant. Then it's minus 5 integral of cosecant squared, that's negative cotan. Okay, plus c. And then you just multiply them out, so 5 cosecant theta plus 5 cotan theta, and that should be the end. and then plus c. So you have to know all your basic integrals again. Hate to go through them again, but all the basic trig integrals, you know, sine theta d theta is negative cosine theta plus c. Integral of cosine theta d theta, of course, is sine theta plus c. Integral of secant squared theta d theta, of course, then is our tan theta plus c. And then on the other hand, then you have all these things like cosecant theta, cotan theta, which is what we were kind of just dealing with above. That integral will be negative cosecant theta plus c. Integral of then secant theta tan theta d theta, of course, is secant theta plus c, and then the integral of cosecant squared theta, which we just dealt with, d theta, is negative cotan theta plus c, right? So hopefully these are just the basic ones. I don't want to go through and repeat everything, but if you look at the 8.1 video, it's basically, I think in the beginning of the video, I go ahead and go through all the ones that you should have memorized. Okay, let's move on to 8.2. So in 8.2, we get integration by parts. So that would be uv minus v du. So let's take a look at a couple of these. Here, the first one, xe to the 4x dx. So we had this acronym LEAT, which was log, inverse trig, algebraic, trig, and then exponentials. So for us, the u part is going to be the algebraic, because that comes first in LEAT. And then the dv will be e to the 4x dx, just everything left. So du will just be 1 dx, so I just write dx. And then v will be the integral of e to the 4x, so that would be e to the 4x over 4. And then I could go ahead and sort of do my arrows, right? So it's u times v, this times this, minus v du, that times that. So I'll have xe to the 4x over 4 minus, and you can factor out 1/4, and then you just have the integral of e to the 4x dx. Okay, so hopefully you can do that second integral then. Again, the integral of e to the 4x will be e to the 4x over 4. And then you could simplify that second term. So you'd get xe to the 4x over 4 minus e to the 4x over 16, and then plus c. Okay, so that one's that's fairly the kind of typical by parts problem. Let's look at a non-typical one. So number 6, we have the integral of 19 arctan of x dx. So this doesn't even look like the typical integration by parts, because there's not really two things inside of the integral, right? There's just the arctan. Let me pull the 19 out first and then deal with that. Okay, so u and dv, right? What you do is pretend that one function is actually just the number 1, because arctan is the same as arctan times 1. So you can always pretend there's like a 1 in here, and then use that for your v, your dv, or your u. Okay. From LEAT, we know the inverse trig comes before algebraic. The number 1 is considered algebraic. Okay, so I'll have arctan of x, and then for dv I'll put the 1 dx. Okay. Once you get over that hurdle, then it should be pretty easy. The integral of 1 is just x. The derivative of arctan x, which I expect you to know, is 1 over 1 plus x squared dx. Okay, then we can go and do our arrows. So this will be equal to 19 times x times arctan of x minus x times 1 over 1 plus x squared. So I have x arctan of x minus the integral of x over 1 plus x squared dx. Okay. Okay, that's really the by parts now is done, because I'm going to be able to do that second integral. I just have to do a u sub, right? So I'll let u equal 1 plus x squared, and then go for my du will be 2x dx, and then my dx will be du over 2x. Okay, so I'll have, after distributing, 19x arctan of x minus 19 times this integral of x over u times dx, which is now du over 2x. Factor out the 1/2, so I got 19 halves. The x's will cancel, and it just leaves me with 1 over u du. Okay, and then I integrate here, so I got 19x arctan x minus 19 halves ln absolute value of u plus c. Get 19x arctan x minus 19 halves ln back sub absolute value 1 plus x squared, and then plus c. Okay. Okay, so yeah, not your typical by parts, but still that kind of problem does come up every once in a while. All right, let's look at one of the ones that is called I think I may have called these loopers in the video. So number 9, the integral from 0 to 2 of e to the x sine x dx. Okay, so with these you have to do by parts twice, and then you kind of get back to where you started, and then you can solve for the integral. Okay, so determine my u and my dv from Liate. The trig comes before exponential, so I do the trig here and the exponential here. The integral of e to the x is just e to the x. The derivative of sine x, cosine x dx. Okay, so there's one by parts. Do my arrows. U times v minus v du. So I have e to the x sine x minus the integral of e to the x cosine x dx. I got to remind myself to evaluate, so I'll put a bracket there. I'm not done with the integration, right? I still need to kind of pull off this integral. So, but the problem is I can't do it unless I do by parts again, so I do by parts again. Okay, so I'm going to do a u here, dv here against Liate. Again, Liate says the trig before exponential. The integral of e to the x is just e to the x. The derivative cosine is negative sine. And then I'm going uv minus v du, u times v minus the integral of v du. So this you don't mess with the first term. E to the x sine x is basically staying the same. And then minus the result of this by parts. So it's e to the x cosine x minus e to the x, the integral of e to the x times negative sine x. So there'll be another negative. I can apply the integral, that will become plus, and then this will be integral of e to the x sine x dx. Okay, I'm going to distribute this negative and equate it to the original integral I started with. So I started with this integral from 0 to 2 e to the x sine x dx. And on the other side, then I have e to the x sine x minus e to the x cosine x minus this integral e to the x sine x dx. Okay, so what happened here, and this is why I call it the looper, we got back to where we started. Okay, so this I'll just take and call it I, and then the same thing for this. Okay, so the next step is to solve for I. So basically what you do is just add I to both sides. So on the left you'll have two i's, two of those integrals, and then on the right you'll just have e to the x sine x minus e to the x cosine x, and you have to remind yourself eventually to evaluate once you isolate the integral. So you divide both sides by 2, You get e to the x sine x minus e to the x cosine x over 2. And we need to evaluate from 0 to 2. Okay, so our integral will be e to the 2 times sine of 2. You probably need a calculator for that if you want. E to the 2 times cosine of 2 all over 2. And then minus the same thing with 0 plugged in, right? So I have e to the 0 times sine of 0, that's just 0. And then minus e to the 0 is 1 times cosine of 0 is 1, so 0 minus 1 all over 2. Of course, that's just negative 1/2, and then you got a negative issue, so your final answer, e squared sine 2 minus e squared cosine 2 all over 2 plus 1/2. Okay. So those are a little harder, but they do come up, and when they do in the context, it's more complicated. These problems become a little harder. So you really do need to know how to do these looper problems and by parts in general. It's one of the main tools in your toolkit. Okay. Okay. 8.3 is on trig integrals. So you should know those Pythagorean identities. The cosine squared plus sine squared is 1, and then 1 plus secant squared is 1 plus tan squared is secant squared, and then 1 plus cotan squared is cosecant squared. Those guys, the two kind of trig identities you might not remember. The cosine of cosine squared theta is equal to 1 plus cosine of 2 theta over 2. Sine squared theta is equal to 1 minus cosine of 2 theta over 2. And then every once in a while, but not often, we have to use the, I forget what they call it, maybe the half angle formula, or the double angle formula. What is it? Sine of 2 theta equals 2 sine theta cosine theta. So you should have all those memorized, plus the Pythagorean identities. All right, so let's get in there and look at where one of the problems where we actually apply those first two identities. Here I have sine to the 4th of 5 theta d theta. Okay. So those first two identities, sometimes call them the power reduction identities. So that's what I want to do. I want to reduce the power from the 4th power to the 1st power. So first off, I could think of sine squared as sine to the 4th, rather, as sine squared squared. And then I could replace the stuff inside the parentheses here with our identity. So this will become 1 minus cosine of, we have to double the angle, so this will be cosine of 10 theta over 2 squared d theta. And then we want to square that thing. So in the numerator I have the FOIL, and the denominator I'll have 4. 2 squared is 4. So the numerator, the first 1 times 1 is 1. The outer and inner will both be negative cosine 10 theta. So adding them together, you get 2 of them, 2 cosine 10 theta. And then finally plus cosine squared 10 theta d theta. Okay. I'm going to break that fraction up. So I'll have 1/4 minus 1/2 cosine 10 theta plus 1/4 cosine squared 10 theta. Whoops. Yeah, that's right. And then all of this in parentheses, d theta. Then I want to apply the power reduction on this last term. Okay, so you always need to get that cosine power down to just cosine to the 1st power. Okay, so in this case, I'll have 1/4 minus 1/2 cosine 10 theta plus 1/4 times 1 plus cosine. If I double 10, it will give me now 20 thetas all over 2 d theta. And then I'll have the integral of 1/4 minus 1/2 cosine of 10 theta plus, and I'm going to sort of distribute the 1/4 and then butterfly it, so I'll end up with 1/8 plus cosine of 20 theta all over 8, and then d theta. Okay. Combine like terms before you integrate, so that first term is really 2/8, and then I combine it with the 1/8, that will give me 3/8. So I have the integral of 3/8 minus 1/2 cosine of 10 theta plus cosine of 20 theta, 1/8 times that, right? And then d theta. Okay, so finally integrate. So the integral of 3/8 is 3/8 theta. And then for integrating like a cosine of 10 theta, all you have to do is integrate cosine. That will be sine 10 theta, and then divide by 10, which you would get naturally if you did a u sub. Okay. Then plus 1/8 times, you'll end up having to divide by 20 this time, and then that will be sine of 20 theta, and then plus c. Okay. From there, you can clean it up a little bit if you want to. So this would be 3/8 theta minus 1/20 sine 10 theta, and then plus 1/160 sine 20 theta, and then plus c. Okay. Okay. Let's look at number 4. So here I have the integral of cosine to the 5th t all over the square root of sine t dt. Okay, so the deal with something like this is you want to factor back a factor of cosine, and then convert the remaining cosines into sines, and then do a u sub for sine. Okay. So here I got cosine to the 4th t all over the square root of sine t, and then times cosine t dt. Then you could rewrite cosine to the 4th as cosine squared squared again. Okay. Instead of writing cosine squared, though, we use Pythagorean identities to write it as 1 minus sine squared. And then that's all over the square root of sine t times cosine t dt. Okay. So here, you know, what do I need to do? I need to now do that sub for sine. And the way I've set it up, by pushing back the cosine or factoring the cosine to the back of the integral, the differential part is just what you see there, the cosine t dt. If you need to, you can solve for dt. That's du over cosine t. Okay, so you'd have 1 minus u squared squared all over u to the 1/2, and then times cosine t times dt, which is du over cosine t. Nice cancellation. And you want to FOIL the 1 minus u squared, so 1 minus 2u squared plus u to the 4th all over u to the 1/2 times du. Okay. Then I'm going to butterfly the thing, so 1 over u to the 1/2 minus 2u squared over u to the 1/2 plus u to the 4th over u to the 1/2, and then du. Okay, set it up for the power rule, so I'd have u to the negative 1/2 minus 2u to the 4/2 minus 1/2, so it's 3/2, and then plus u to the 8/2 minus 1/2 is 7/2, and then power rule and back sub. Okay, so I got u to the negative 1/2 plus 1 is 1/2, and then divided by 1/2 is the same as multiplying by 2. U to the 3/2 plus 1 is 5/2, and then multiply by 2/5, plus u to the 7/2 plus 1 is 9/2, and then multiply by 2/9, plus constant, and then finally clean it up and back sub, right? So you got to plug sine t back in, which is relatively painless. And there we have it. Okay. Okay. Let's look at number 7. I just want to look at number 7 because we had something similar to this on that first test. And hopefully now that you see it again, it'll be like, oh, that one's easy, right? I can handle that. Okay. So it's the Pythagorean identities again. Tan squared is equal to secant squared minus 1. And then you can integrate each part of that. So the integral of secant squared is tan x. The integral of 1 is x. And I'm going to go from 0 to pi over 3. So the tan of pi over 3 is just root 3. And then minus pi over 3. And then if you plug in 0, tan of 0 is 0. Plug in 0 for x, that's just 0 as well. So that's your final answer. Okay. All right, let's move into 8.4 then. So 8.4 is basically just the application of all of those trigonometric integrals. There were 3 types of substitutions here. You should know how to do each type. So if you had a squared minus u squared, that would force you to have the sub u equals a sine theta. If you have the square root of a squared plus u squared, that would force you to use u equals a tan theta. If you have the square root of u squared minus a squared, that would force you to use u equals a secant theta. Okay, so let's dive in here and look at problem 3. So I have the integral of x squared minus 25 square root of all over x dx. The integrals on my test will be in the same order as you see here. So you should kind of know, all right, this is going to be, kind of your generic integral. The next one is probably going to be some sort of by parts, maybe 1 or 2 of those, and then maybe, a couple trig integrals, and then trigonometric substitution, right? So they're in order, the same order as the book, as my lectures. So hopefully that's a pretty big hint as to what method you're probably going to be using. But there could be several problems that are trig type problems, and then you go to the trig sub. So, but they are in order. Okay. So, anyways, here the form tells me it needs a secant sub. So, this case u is just x, and then the a value is 5. So then I like to get all my information, 5 secant theta tan theta d theta, and then build my triangle. So I need theta, that will be secant inverse of x over 5. And then I go to my triangle. So secant is 1 over cosine, right? So we're looking at hypotenuse over adjacent. So hypotenuse x all over adjacent 5. Use Pythagorean theorem to get the third side. So this ends up being x squared minus 25. And then you could start doing your substitutions. So it's just that the first 2 things first, right? So you have the integral of the square root of x squared, which is 25 secant squared theta, minus 25 all over x, which is 5 secant theta, and then times dx, which is 5 secant theta tan theta d theta. Okay. This radical thing, you use Pythagorean identities to simplify it. First I'll factor out the 25, and I'll have secant squared theta minus 1. Then that'll equal the square root of 25 tan squared theta. And then you could write that as 5 tan theta. Okay. On top of that, you have a little bit of cancellation. These 5 secant thetas are gone. So we're getting the integral of 5 tan theta times tan theta, which is tan squared theta d theta. Okay, if you got the last problem right, then you should get this problem. Tan squared, we're going to convert the secant squared minus 1 using another Pythagorean identity. And then we should be able to integrate those, right? So it'd be 5 tan theta minus theta plus c. So this will be 5. I'll go ahead and distribute the 5. 5 times tan theta. Tan theta, now I go back to the triangle. So tan is opposite over adjacent. So this will be 5 times the square root of x squared minus 25 all over adjacent, which is 5. And then minus 5 times theta. And unfortunately, we just have to stick with the secant inverse here. Okay, and that's pretty much it. You clean it up by canceling out the 5's. But that's more or less the answer. Let's look at number 5. So this will be a tan version of that problem. 6x squared all over 36 plus x squared squared. Okay. So that denominator has that form a squared plus u squared. Okay, so in this case the u is x, the a is 6, and the form, because it's a plus, indicates you have to use a tan theta. Get your dx part, so that would be secant squared theta d theta. Solve for theta, so theta is going to be equal to tan inverse of x over 6, and then get your triangle. Okay, so again, tan is opposite over adjacent, and then this third side is going to be the x squared from the Pythagorean theorem, x squared plus 36. So you use those first two parts to populate the integral in terms of theta. I'll have 6 times 6 squared tan squared theta. So it's really 36 tan squared. I'll just write 6 times 6 squared, so I don't have to multiply out big numbers, is basically what I'm doing. That'll be all over 36 plus 36 tan squared theta. And then dx is 6 secant squared theta d theta. Okay, in the numerator there are 4 factors of 6, so that would be 6 to the 4th. Then we have a tan squared theta, secant squared theta, all over something d theta. So what is that something in the denominator? So this thing is going to be, factor out the 36, you get 1 plus tan squared theta. And of course this thing is squared. I lost my 2 there. It should be squared like that. Okay. Then use Pythagorean identity to rewrite this. And I'm going to write 36 as 6 squared. Hopefully that didn't confuse anybody. But then 1 plus tan squared is secant squared theta, and then we want to square that. Okay. So 6 squared squared is 6 to the 4th, and then secant squared squared is secant to the 4th. And so you see, well, that'll work out nice. 6 to the 4th over 6 to the 4th, those will cancel. Then you have secant to the 4th theta. So I'll end up with tan squared theta all over secant squared theta d theta. Okay. From this point we convert everything into sines and cosines. So tan squared is really cosine squared over sine squared. 1 over secant squared, well, hey, that's the same as cosine squared. Right? Oops, I'm sorry, tan squared is sine squared over cosine squared. Yeah, so 1 over secant squared then is just cosine squared. Let's write it cosine squared over 1. And then your cosine squares will cancel and you just have the integral of sine squared theta d theta. Okay. At that point you're stuck with that sine squared theta. So you use one of the power reduction formulas, 1 minus cosine 2 theta over 2. and then you want to butterfly that guy into 1 over 2 minus 1 over 2 cosine 2 theta, and then finally we can start integrating. So I'm going to get 1/2 theta minus 1/2 sine of 2 theta over 2. So I got another factor of 1/2 if you do the u sub. Okay, so I can back sub now the theta. So it's 1/2. Theta is tan inverse of x over 6. Okay, that's just looking back at the box above on the left. The troublemaker is that sine 2 theta. Okay, and it's because we need the angle just to be theta, not 2 theta, right? So what you do is use the I think it's called the double angle formula. Sine of 2 theta is really 2 sine theta cosine theta. All right, so you'd have 1/2 tan inverse of x over 6 minus 1/2 sine times cosine. So sine is opposite over hypotenuse, like that. And then cosine is adjacent over hypotenuse. If you want to, you leave it like that. That's fine. I don't mind. Okay, so that's always the super hard one, because there's the a little bit of this trig fancy footwork to get the sine squared, and then you got to do a power reduction formula, and then you're stuck with the sine 2 theta, so you have to do another transformation using trig identities, and then finally you can get back to the in terms of x. Okay, 8.5 is partial fractions, and there's basically those 4 types. So linear, linear repeated, irreducible quadratic, and repeated irreducible. Okay, so let's look at number 4. So the numerator here, 12x squared plus 9x minus 2. All over the denominator is x cubed plus x squared. Okay, dx. Okay, so the first thing I want to do, assuming the numerator's degree is less than the denominator's degree, and on the test I'll make sure that's true. You won't have to worry about it. But on the WebAssign, there was one question where that numerator degree was actually greater than the denominator, and then you had to do long division. Okay. So here the numerator's degree is 2, the denominator's degree is 3. I can do the partial fractions. Okay, so I'd have 12x squared plus 9x minus 2 all over, and you got to factor it. So you'd have x squared, which is repeated linear, and then times x plus 1. So you need 2 fractions for the x squared, and then you need 1 fraction for the x plus 1. So for repeateds, you work up to the exponent. So if it was x cubed, you'd need another fraction over x cubed. And the numerator for linear factors, you just put constants, a, b, c, d, whatever. Okay, then I'm going to multiply both sides by the denominator on the left. So here x squared times x plus 1. And if you do that on that side, you have to do it on this side. Okay, so on the left I have 12x squared plus 9x minus 2. On the right, distributing. The first distribution, one of the factors of x will cancel, and I'm left with a times x plus 1. The second distribution, the x squared factors will cancel, just leaving you with b times x plus 1. The third distribution, the x plus 1's cancel, leaving you with c times x squared. Okay. Okay, so for this you can do substitution. You could start saying, all right, I want to let x equal, 0. Okay. So on the left, when you plug in 0, you'll get 0 plus 0 minus 2. On the right, you're going to get a times 0 times 1, which will be 0, plus b times 0 plus 1 is 1, plus c times 0. So you get negative 2 equals a plus b. Whoops. The a will cancel out, right? A times 0 is just 0. A times 0 times 1 is just 0. So you just get b is negative 2. All right, let's move over here to the negative 1. So now I'm going to put in negative 1. So I got 12 times negative 1 squared is 1, plus 9 times negative 1 minus 2. And on the right side, I'll have a times negative 1 times 0 plus b times 0 plus c times negative 1 squared. Okay, so on the left I have 12 minus 9 minus 2. On the right, this will be 0, this will be 0. You just have c times negative 1 squared. Negative 1 squared is 1, so you just have c. So c will equal 1. Okay, then you could just pick any x value you want. We'll pick x as 1 for the sake of sanity. So I have 12 times 1 squared is just 12. 9 times 1 is 9 minus 2. Then you'll have a times 1 plus 1, which is 1 times 2, which is 2, plus b is negative 2, times 1 plus 1, which is 2, plus c, which is 1, times 1 squared, which is also 1. Okay, so 12 plus 9 is 21, minus 2 is 19. This is 2a minus 4 plus 1. So I have minus 3 there, add that to the other side, and you get 22 equals 2a. So a is 11. Okay, so that's our partial fraction decomposition. You use all of that information then to rewrite our original integral. Okay. So I'm trying to quarantine all that. So the original integral will become a over x, in other words 11 over x, minus 2 over x squared, and then plus c, which is 1, all over x plus 1 dx. Okay, so I'm literally replacing this integrand with this thing, with a, b, and c filled in. Okay, so now I do integrals of all three. The first integral is just 11 ln absolute value x. The second integral, you can factor out the 2, and then have the integral of 1 over x squared, which is really x to the negative 2. And then the third integral is just going to be an ln of x plus 1, right? You could do a u sub if you want. You can do a u sub, why not? Right, so you get u down for x plus 1, and this will be du. Dx is just du. And then integrate those two guys. So ln absolute value of x minus 2. X to the negative 2 plus 1 is negative 1, divided by negative 1. I'm going to clean that up here in a sec. Plus ln absolute value of u plus c. So I get 11 ln absolute value of x. Negative negatives, a plus 2 over x. Get rid of that negative exponent. Back sub ln absolute value x plus 1 plus c. Okay. Let's look at one that has a irreducible quadratic in it. So problem 9. So the integral from 1 to 3 of x plus 1 all over x times x squared plus 1 dx. Okay. So the denominator is already factored. I'm just going to do my setup now for my transformation, my partial fraction decomposition. So x is linear, so I need one fraction there. The x squared plus 1 is quadratic. I need one fraction for that. Neither are repeated, so they only need one fraction each. And the numerator of x, because it's linear, you can just put an a. And the numerator of x squared plus 1, because it's quadratic, you have to put a linear factor, bx plus c. Okay. So again, you go through and solve for a, b, and c. I'm going to multiply both sides by x times x squared plus 1. On the left, the denominator will cancel with that multiple of x times x squared plus 1, and you just have x plus 1. On the right, you have to distribute. In the first distribution, the x's will cancel, leaving you with a times x squared plus 1. In the second distribution, the x squared plus 1's will cancel, leaving you with x times bx plus c. Okay, when you have these irreducible quadratics, then you have to do equating coefficients. So on the left, if you need a placeholder for x squared, you can put 0x squared and then plus x plus 1. On the right, I'm going to go ahead and multiply everything out. So I get ax squared plus a plus bx squared plus cx. If you want to group like terms together and make it easier, you can do that. So I'd have ax squared plus bx squared plus cx plus a. And then start equating coefficients, right? So the x squared portion here, you can rewrite it if you want, a plus b x squared. So the a plus b on the right has to equal the 0 on the left. The coefficient on over here on x squared, which is 0, has to equal the coefficient on x squared on the right, which is a plus b. Okay, then do the x part. So the coefficient on the left is 1. The coefficient on the right is c. So c must equal 1. And then finally do the constant terms. So a looks like it's equal to 1. And then go and solve for b. So you can do a back sub here for b. And you get 0 equals 1 plus b. So b is negative 1. Okay. Okay, so that's our partial fraction decomposition. Now we rewrite our integral. So plug in a, you get 1 over x, plus, I guess we have negative x plus 1 for c, all over x squared plus 1 dx. Be a little careful with that negative and that numerator there. Make sure it's not floating in front of the fraction. That would indicate that you actually need to distribute the negative through the numerator. Written right now, what they usually do, and you'll see this in the book, is not to write it that way. It's just to write it 1 minus x. Okay. That way you don't have to worry about people thinking the negative is out here, and that would be wrong. Okay, the first part of the integral, you can do that. It's ln of absolute value x. The second integral, though, you're going to need to butterfly it, right? So it'll turn into two integrals. The first one, 1 all over x squared plus 1, is an inverse tangent. And then minus the integral of x all over x squared plus 1 dx. So as noted, the second guy is just an arctan with u equal to x, and then a equals 1. So it'll be arc1 all over 1, arctan of u all over 1, and of course u is just x. X over 1 is just x. So it's just arctan of x. Minus then this other guy. And this other guy you're going to have to do another u sub. So u is x squared plus 1. And du will be 2x dx, and then dx is du over 2x. So be minus the integral of x over u times dx, which is du over 2x. Okay. So I get rid of these x's, factor out the 1/2, integral 1 over u du. Of course, that's the ln of the absolute value of u. Back subbing, you get x squared plus 1, and then plus c. Whoops, we were supposed to evaluate that guy, weren't we? Yeah, sorry. So there's no plus c. We have to evaluate. So evaluate from 1 to 3, and you could just get an approximation on your calculator, but it'll be ln of 3 plus arctan of 3. Those are the ones I need my calculator for. minus, I need my calculator for this one, ln of 9 plus 1 is 10. And then minus ln of 1 is 0. Arctan of 1 is pi over 4. And then minus 1/2 ln of 2. And if you plop that into your calculator, you'll end up with 0.758 to 3 decimals. Okay, so that's the partial fraction decomposition. The next section was Lapital's rule. So you should be able to do basically the generic Lapitals plus the 3 sort of other indeterminate forms. So an example of the generic Lapitals is like number 6. Okay. If you take the limit as x goes to infinity in the numerator, it'll go to infinity, e to something really big eventually. Okay. And the denominator is 6 minus x to the 6. That's going to be negative infinity eventually. So it has that infinity over infinity form. Okay, so you could do Lapitals. If it's infinity over infinity or 0 over 0, that's Lapitals. Okay. So the derivative e to the x to the 5th is e to the x to the 5th times the derivative of x to the 5th, which is 5x to the 4th, all over negative 6x to the 5th. The derivative of the 6 is 0. Clean it up a little bit. I'm going to bring the negative upstairs. So I have negative 5e to the x to the 5th all over 6x. Okay, now the numerator is going to negative infinity and the denominator is going to infinity. And how do you figure that out? You just plug in some numbers going to infinity, like plug in x is 10, x is 100, x is 1,000, x is 1,000,000, and you'll get something negative really big in the numerator and then something positive really big in the denominator, like 6 times 10, 6 times 100, 6 times 1,000, that sort of thing. Okay, so it's in that form. I could do Lapital's again. So I got negative 5 e to the x to the 5th times the derivative of x to the 5th again, which is 5x to the 4th. And then that will be all over. Seems like I screwed something up. Oh, I lost my to the 5th power right there. I'm sorry. Well, no, I didn't, because there was that cancellation, right? So it'd be just over 6x. Okay, well, whatever. I must have got it wrong in my notes. Anyways, the derivative of 6x then is just 6. Okay, so we got this monstrosity. In the numerator, basically you just have a bunch of stuff being multiplied together. So if you plug in 10, you'll have e to the 1 with 5 zeros, which is a huge number, times 5 times 10 to the 4th, which is a huge number. That numerator is going to go to negative infinity. Okay, and then dividing by 6 isn't going to do anything except slow it down a bit. So you'd end up with negative infinity at the end of the day. Okay. So when in doubt, you can always kind of do a table of values going to wherever you need to go. So in this case, infinity. And I usually just do this sort of thing in my head. So you'd get like negative 5 e to the 10 to the 5th, which is already a huge number. And then times, I ran out of room, times 5 times 10 to the 4th. Right? So if you multiplied that all out, this thing is huge. If you plug in 100, it's even bigger. And it just gets really, really, the calculator won't even be able to evaluate that 1,000 into that expression in the numerator. So it's just going to get huge. It's going to be negative, so negative infinity. Okay. Let's look at number 9. So we get the limit as x goes to infinity of x sine of 7 over x. Okay, so this form, if you let x go to infinity, that thing will be infinity, and then if you let 7x go to the x go to infinity, you'd have 7 over something huge, which would be like 0. So this would be like a 0 here. And sine of 0 is just going to be 0. So it's infinity times 0 form, and what you had to do there was turn it into a fraction. Okay, so you get the limit as x goes to infinity of sine of 7 over x all over 1 over x. Then you could recheck the form and note it's a 0 over 0 form. Okay, so you could do Lapitals. So the limit as x goes to infinity, I'm going to need the derivative of 1 over x. So I'll do that over here on the left, bottom left. 1 over x is x to the negative 1. The derivative then is negative x to the negative 2. Right? So in the denominator, that's what I have, negative x to the negative 2. In the numerator, the derivative of sine is cosine. And then the derivative of 7 over x will just be negative 7x to the negative 2. Okay. The nice thing about this then are those x to the negative 2's will cancel, and you'll have negative 7 over negative 1, which is positive 7. And then you could just evaluate it by evaluating first 7 over x. That will turn into 0, and then cosine of 0 is 1. So you would have 7 times 1, which is 7. Okay, so I'm using a lot of stuff that we learned in the videos. Basically, L over infinity is always going to be 0. L over 0 is always going to be either plus or minus infinity, and you have to do like a test value to figure that out. So number 14, we see some L over 0's. I have the limit as x goes to 2 from the right of 8 all over x squared minus 4 minus x all over x minus 2. So that first term in there is one of those L over 0's, right? And we can sort of separate it and just look at it individually. Okay. So where does that thing go? Because it's L over 0, so if you plug in 2, you'll have some number L, and the bottom you'll have some, it'll just be 0, right? 2 squared is 4, minus 4 is 0. So the way you dealt with those is to kind of, remind yourself your approach. So I'm coming in from the right. That means I'm thinking x values like 2.1, 2.01, 2.001. I'll just think of 2.1. Then I plug the 2.1 into that expression, the 8 over x squared minus 4, and determine if it's plus or minus. So the 8 is positive. 2.1 squared minus 4 is also positive. 2.1 is bigger than 2, so when you square it, it'll be bigger than 4. Okay, positive over positive is positive, so this part is positive infinity. The other term, the x over x minus 2, you can kind of play the same game to figure out where it goes. So again, we're thinking values like 2.1, 2.01. So if I have 2.1 here, plugging 2.1 into x over x minus 2, I get a positive over 2.1 minus 2 is a positive again. So this goes to infinity. So overall, the form is infinity minus infinity, which is indeterminate. Okay. So the transformation you want to do here is to take two terms and make them into one. And so if you factor the first denominator, you see it's x minus 2 times x plus 2. So that to turn this into one fraction, and the second denominator, you just multiply top and bottom by x plus 2. Okay. So I end up with the limit of, as x goes to 2 from the right, of 8, and I'm going to distribute that negative x through. So I get minus x squared minus 2x all over the common denominator, which I'll just write as x squared minus 4. And then investigate the type again. So if you plug in 2, you'll get 8 minus 4, which is 0. You plug 2 into the bottom, you get 4 minus 4, which is 0. So you could do Lapitals. Derivative of 8 is 0. Derivative of negative x squared is negative 2x. The derivative of negative 2x is negative 2. And the denominator, the derivative of x squared is 2x. Derivative of negative 4 is just 0. Okay. And then we try another substitution, see if it works. So plugging in 2, you get negative 4 minus 2 is negative 6. On the bottom, 2 times 2 is 4. And that should be our answer, negative 3/2. Okay. So those are two types. The third type is the hard one, the exponential type, number 11. So we have the limit as x goes to infinity of x to the 8 over x. So the way I do it is convert this into an exponential. So I'll have e to the ln of x to the 8 over x. Then I'm going to move the limit into the exponent and use the power rule for logs to bring the 8 over x in front of the log. So you'd have 8 limit as x goes to infinity of 8 over x times the ln of x. Then this form as x goes to infinity is actually 0 times infinity. It's pretty easy to turn into a fraction, though. You just are going to go limit as x goes to infinity of 8 ln x over x. And then that form is infinity over infinity. Okay, so you could do Lapitals to it. Okay, so the derivative of ln of x is 1 over x. So in the numerator I have 8 over x. And the denominator of the derivative of x is just 1. So you just get 8 over x. 8 over x is that L over infinity form, and that's just equal to 0. So you'll have e to the 0, which is 1. Okay, so the reason why we did all these Lapitals and infinite limits stuff was because of chapter 8.8 with improper integrals. And there were two main forms of improper integrals, the infinite interval and the infinite discontinuity. So we want to see one of each on the test. So first one is an infinite interval. You could tell because of that infinity symbol. Okay, so what you do is change it into a limit approaching the bad part of the integrals. So that infinity symbol, we get rid of it and just take the limit as we approach infinity of this integral evaluated from 1 to b. Let me rewrite the integrand to be 3x to the negative 1/10 dx. Okay, so I'll go ahead and integrate. I have 3 x to the negative 1/10 plus 10/10 is 9/10, and then times 10 over 9. Clean it up a bit. So I have 10/3 x to the 9/10, and I need to evaluate it from 1 to b, and then take the limit. So I get the limit as b goes to infinity of 10/3 plug in b to the 9/10 minus 10/3 plug in 1 to the 9/10. 1 to the 9/10 is 1. Okay, so if you plug b values in and the b value is going to infinity, eventually b to the 9/10 will also go to infinity. Okay, you can just put in like 10 to the 10/9, and then when you plug it in b to the 9/10, it'll be like this, and that'll just be 10. Then plug in 100 to the 10/9, and when you plug it in, you'll just get 100. So then 1,000, 1,000,000, 1,000,000,000. So that first term is just going to go to infinity. And then it'll be minus just whatever, some number, which doesn't really affect the overall limit. So in the end, it's just going to go to infinity. And make sure you note that this is divergent. Okay, so the infinite discontinuity type is usually where the issue in the integrand will be a division by 0. Okay. So here I have 2 all over the square root of 7 minus x dx. Right? So where is the issue here? That's 7. If you plug 7 into the denominator, it will be 7 minus 7, which is 0. Square root of 0 is 0. 2 divided by 0 is undefined. So the issue is at 7. Here's 0. Here's 7. So what we're doing then is replacing 7 with a limit and taking the limit as we approach it. All right, so approach 7, we want to approach from the negative direction. So make sure you indicate that on your limit. And then we're going 0 to b, and let me rewrite my integrand as 2 times 7 minus x to the negative 1/2 dx. Okay, so I need a u sub on the 7 minus x. So du will be negative dx, and then dx is negative du. Okay. So here I'll have a limit of the integral of 2 times u to the negative 1/2 times dx, which is now negative du. I can factor out that negative, and I'll have negative 2, and then integrate the u to the negative 1/2. That will be u to the negative 1/2 plus 1, which is positive 1/2, times the reciprocal of 1/2. And then I want to back sub and evaluate. So back subbing everything, I'll have limit as b goes to 7 from the left of negative 4 times 7 minus x to the 1/2. And then they want to evaluate this from 0 to b. So this will be the limit as b goes to 7 from the left of negative 4 times 7 minus b to the 1/2 minus negative 4 times 7 to the 1/2. Okay. All right, maybe clean it up a little. I got carried away with the fraction, with the parentheses. So this is negative 4 times 7 minus b to the 1/2 plus 4 times 7 to the 1. Let's just write root 7, shall we? Okay, so if you substitute in 7, that first term will just be 0. So you'll just end up with 4 root 7. And that's convergent then, and that's your answer. Okay, so a lot of integration. What you could do is find the similar problems in WebAssign, do practice similar, and then once you kind of master all these types of problems, go back to the question pool and start chugging away through those problems. Look for the ones you don't know how to do, and then hopefully you'll do well on the test. Okay, so as usual, thank you for watching, and I will see you next time.